If you have.
Welcome to Monday, May 8th, Astro Cafe. We have a full agenda this evening, and we'd like to start with Aimee Rossen, who is going to talk about our RASC volunteers at star parties. Hi, Aimee.
Hi, Margie. Nice to see you. Nice to see everyone. Some faces I haven't seen just yet. So as Margie said, my name is Aimee Rossen. I'm going with the term factotum of the center of the universe. So I do a little bit of everything, and one of those things is kind of organizing volunteers and getting that guest list ready to go every week. So I just wanted to talk about a couple of things. So the first thing is about a year ago, we started doing volunteer waivers. And so we have them on the Hill, and then I can also send them via email. It's really just to kind of get everybody on the same page in terms of safety, because as you know, the NRC is a stickler for safety on that hill, as we should be with only one road up. The other thing is the volunteer list. So I have a general volunteer list. I see some familiar faces every week, so I just have kind of added them to our ongoing roster. But we really do want you all to feel welcome to come up at any star party. So what I've put on there at the bottom is a little asterisk, and it just says if anybody identifies themselves as a RASC volunteer, just to let you up. So if you're not on the list, you haven't talked to Lauri, haven't talked to me, that is okay. Come on up. Just let them know that Aimee said that you're allowed to come up, and that'll be no problem at all. And so really that's it. Don't want to take too much of your time, but just so you know who I am, even though my screen is really blown out. I'm sorry, I can't get the lighting any better. And I'm pretty much there at every single star party. I'm inside near the main desk, kind of running back and forth. So if you haven't met me, come say hi. I'd love to meet all of you. And again, yeah, if you want to come up and you're not on the list, don't worry, just come on up. And that's really all I have to say. So thanks for having me.
But I think, Aimee, we want to make sure that people have got the waiver signed to be a volunteer on the Hill on the Saturday night. So if you did it last year, it's okay. Like, you're fine. But if you have not done that, then we really would like to. We're just kind of trying to keep track of who we have up on the Hill, and that you all have been able to see the safety video, and everything is kind of is okay on that side. And for those of you that don't have keys or passes to get up on the Saturday nights, if you can come up before 7 o'clock, then or just before 7 o'clock, then you will not be in the way of the cars that are kind of lining up of the public that are coming through. And we have certain places for our volunteers to park, because there's only 18 spots up at the top of the hill for the visitors. And so we want to keep those specifically for the public. So the volunteers have got places behind the White House, down in the little kind of section down as you're coming into the parking lot. It's kind of down onto your left. We also can park at the VCO. So there's other places, but we just like you to tuck yourselves in so that you're not taking up a space up in the front. Now, obviously, if you've got equipment, then you can definitely put it up, get your equipment out onto the deck, and then just move your car back to another spot. And if there's any questions, Amy's really the one with the FDAO that kind of knows the ins and outs of all the volunteering, and she's the one who takes all the names. So if you don't know Aimee, we just wanted to make sure that she was a familiar face to you. So,
and if you don't have our email address, even if you just go to the info@Center of the Universe, those emails get directed to most people, but I will jump on them right away to answer them.
Yeah. Does anybody have any questions for Aimee? Well, that was easy.
Yes, exactly.
Thank you very much, Aimee.
Okay,
Thank
great.
you.
Next, we have Dr. Justin Albert of the University of Victoria, Department of Physics and Astronomy. I have some information about Professor Albert, and here it is. Justin Albert is a professor in the Department of Physics and Astronomy at UVic. He completed his undergraduate studies at Harvard and his PhD at Princeton University in 2002. After his PhD, he was a Millikan postdoc fellow at Caltech. He has been at UVic since 2006. Professor Albert is heavily involved in 3 major research effort areas in physics around the world. 1, the ATLAS experiment at CERN in Switzerland, where his work in searching for and measuring the properties of the Higgs boson addresses the question of the source of the mass of fundamental particles in the universe. 2, co-founding of and current senior leadership positions on both the Altair and Orcasat projects, which produce calibrated light sources to fly on high altitude balloons and in space to calibrate ground-based telescopes in order to address the question of why the expansion of the universe is accelerating. And 3, the Babar experiment at the SLAC National Accelerator Laboratory in California, where his work addresses the question of why the universe is made of matter rather than antimatter. Please welcome Professor Justin Albert.
Thank you very much. Thanks. So today I'm going to talk about number 2 of those 3 things, which is in particular Orcasat. So Orcasat is a small satellite about the size of a tissue box that was launched last year, back in November 26th of this past year, 6 months ago, from Kennedy Space Center, after being, of course, built right here on campus at UVic, and then just as importantly, calibrated at NRC in Ottawa. So calibrated at the so-called spectrum radiometric calibration facility on the Montreal Road facilities there in Ottawa, and then taken across the border by a company called NanoRacks, and shipped down to Kennedy Space Center, where it was loaded onto a SpaceX rocket, Falcon 9, and launched up from Kennedy Space Center to the International Space Station. It sat for a month on the International Space Station, not turned on, of course, just there in their temporary storage. And then it was deployed to its home for its unfortunately, for a short period of 6 months into orbit. And it is currently in low Earth orbit, about 350 kilometers above the surface of the Earth. It makes one orbit around the Earth about every 100 minutes, moving along very quickly, over 7 kilometers per second. And it is in operation. And I will show you, we've gotten some images of it, not as many as we'd like, but one very good image taken at the Blanco telescope in Chile that will be very useful for analysis. So analysis will follow, right now until it burns up in probably at the end of this month. We don't know exactly when, but close to the end of this month, it is spiraling slowly in, and that slow is going to get very quick all of a sudden around the end of this month, and it'll just burn up. And bye-bye Orcasat, no more Orcasat after that point. Of course, then we'll still have the data and we'll complete the analysis of it. That's the in a couple of sentences, that's the status. So why did we do this? So actually use slideshow. I think you're seeing everything there. That's better. So this story begins, really it doesn't begin, it begins a lot earlier, but modern cosmology can be said to have begun in 1929 when Edwin Hubble discovered and published the fact that the universe is expanding way back in 1929. Now, how did he do this? And that's where the story gets even earlier. It doesn't really begin with Hubble. You could go back as far as you'd like in history, but really, perhaps my slides should start with Henrietta Swan Leavitt in the late 18th century, who discovered that a certain type of star called a Cepheid variable star, the most common Cepheid variable, or most well-known Cepheid variable star that we see in the sky is Polaris. Polaris is a Cepheid variable star. But there are Cepheid variable stars are fairly rare, actually. They're a rather bright type of star. They're a giant, bright, hot type of star. But the really interesting thing for usage in cosmology about Cepheid variable stars is that their amplitude, their variability, so they have an amplitude of variability, the magnitude, amplitude of that change in magnitude is related to the period of the oscillation. So the periods tend to be of order 1 month, thereabouts. And so what that tells you, so let's say you find a Cepheid variable star in some other galaxy, and you measure its period. That's easy to measure. You just look at how it's brightening and dimming over time. But then you use that fact, and the fact that use that measurement and the knowledge of how the period relates to that that amplitude of the magnitude oscillation, to know how so that tells you how how bright the absolute magnitude oscillation, but you're measuring also the apparent magnitude on the ground here. So if you know both the absolute magnitude or even an absolute magnitude difference between high and low, and you know an apparent magnitude difference, you can tell how far away that thing is. So it's a standard type of standard candle. You know how bright it is because you've measured its period, unless you've determined through that relationship between the period and the amplitude of its magnitude oscillation. You determine, you know how far away that Cepheid variable star is, and thus you can find how far away its host galaxy is. So so that's critical. As you know, being astronomers, it's when you look out on the sky, you don't see how far away things are. It's the distances are really, really hard. They're the most derived parts of astronomy, in that there's a lot of steps you need to follow to determine how far away something is. You can determine how fast something is moving away from you. That's not hard. That you look at its spectrum and you look at the lines in the spectrum and see how it's redshifted. But and also you can see, you can determine proper motion, the astrometric shifts as a function of time of stars, galaxies, if the galaxies have any, as functions of time. But determining how far away something is, that's really hard. So using Henrietta Swan-Leavitt's determination, and the way she determined that, by the way, is even though Cepheid variable stars are not very common, there are enough of them in the Milky Way galaxy, and even nearby enough within the Milky Way galaxy, such that even back at that time, you could get parallaxes to at least 20 or 30 of them and see this relationship. And that's what Henrietta Swan-Leavitt found. And then Hubble extended that by looking for Cepheid variables in other galaxies. Really, they were only starting to be called galaxies. They were really called nebulae at that time because it wasn't clear really how far away they were. But Hubble's measurements helped tell us that. You could see how far away something is. So this is the distance on the x-axis and the velocity on the y-axis from Cepheid variables within nebulae that Hubble could find. And you see an approximately linear relationship. It doesn't hold so well right nearby the Milky Way because there the expansion of the universe is kind of counterbalanced by gravitational attraction between, for example, Andromeda. Andromeda is actually moving toward us. It'll be below the x-axis here. It's going to be negative because of the gravitational attraction from the Milky Way and Andromeda. But if you go far enough out, beyond the local cluster, out into the rest of the supercluster, you can start to see what is known today, usually goes by the term, the Hubble flow. So the Hubble flow is the large-scale expansion of the universe when one looks at faraway galaxies. So on this x-axis is that distance gotten by Henrietta Swan-Leavitt's period magnitude relation for Cepheid variables. And on the y-axis is redshift in terms of a velocity per what Hubble believed velocity per second at that time, 500 kilometers per second. That is what he found. Now, he was right, of course, that space was expanding. Of course, the slope that he got was actually quite wrong. It was almost 10 times too high, and that cosmology is rife with, and astronomy in general is rife with that kind, those kind of effects. Because how can you really be sure when you look out at a distant galaxy and see what a variable star toward the edge of it? How can you really be sure that that's a Cepheid variable star? There are a lot of types of variable stars, and Cepheid variables are pretty rare. Other types of variables, notably the W Virginis variable stars, contaminated his measurements, and a lot of the ones that were really, indicated a really huge velocity were just other types of variable stars, not Cepheid variables. Nevertheless, Hubble overall was right, and even modern all the way through to the Hubble Space Telescope. Not yet has this been done Cepheid variable wise with JWST yet, but certainly with Hubble and what was called the Hubble Key Project, Hubble's results were repeated in a lot more precise way with Cepheid variable stars. And of course, the slope got a lot smaller, but of course it was still positive slope. The universe is still expanding, and so in that way, his results have certainly held up. Oops. So, before I go further, how do we, Hubble Key Project using Cepheid variables is the way to get cosmology in terms of how the universe is expanding in the medium distance, what we could say. So these are pretty big distances. 2 million parsecs is not a small distance, but nevertheless, in terms of the observable universe, it is pretty small. But what happens if you look out to even more distant galaxies and look for Cepheid variables, variable stars in them? Beyond now we can go a little further with Cepheid variable stars, but once you get beyond 10 to the 7th parsecs, redshift. This that seems big, but that's only a redshift of maybe about 0.1. Then galaxies are just blobs at that point. You don't see any, and you can't resolve any individual stars in them, even these bright Cepheid variable stars. So to go beyond 10 to the 7th parsecs and extend this, what appears to be a line, beyond that point, you need something even brighter. You need another type of standard candle, which is brighter. And fortunately, type 1a supernovae are very bright and fortunately reasonably at least standardizable candles as well. They themselves can, you can match them up, climb the rungs of the distance ladder by matching them up with, or matching up the slope that you get with Cepheid variable stars in overlap regions where you can both still resolve Cepheid variable stars, but also can get a sufficient number of, find a sufficient number of supernovae, or type 1a supernovae, and then extend it out further with type 1a supernovae. So, what is, I'll just say one sentence on what is a type 1a supernova? Well, supernovae in general, I'll start with supernovae in general. They're different causes, but supernovae in general in the Milky Way galaxy, they occur about once per century. The most recent one in our local neighborhood, closer than Andromeda, was in 1987, supernova 1987A in the Large Magellanic Cloud. That was the last eye visible supernova, and it was, what is it, almost not 35 years ago, somewhere around there. We're overdue. And the last one within the Milky Way itself was a few hundred years ago. We're kind of overdue for a galaxy, but you don't want to fall into the gambler's fallacy and say that must mean we'll have one next year or something. The average, average rate is once per century. So hopefully in our lifetime we'll see one. When one occurs within the Milky Way, it should be, likely will be even visible in daytime. Now, that doesn't mean if there's any danger from it, but they're really bright things. The last one in the Milky Way, a few hundred years ago, was visible at daytime, and a lot of caused a lot of interest in astronomy. But they're dramatic events, but pretty rare. Now, type 1a supernovae occur, a better term for them is white dwarf supernovae. The most common picture of a type 1a, i.e. white dwarf supernova, is matter accreting onto a white dwarf from a companion star. Now, that's not an uncommon thing. In fact, most stars in the universe, it's not a huge majority, but the majority of stars in the universe have a companion. The sun is a little bit slightly unusual in that it's not a binary or multiple system. White dwarf, it's not uncommon at all for a white dwarf to have a companion star, and even for that companion star to be fairly nearby. Now, when white dwarfs, when that companion star is nearby, a white dwarf is a very dense, small thing. It's about the typical white dwarf is about the diameter of the Earth, but has the mass of the sun or more in it. So it will tend to accrete, tend to gravitationally attract and suck material off another star. We see this happening. Those are called Roche lobes. You can even see them with a sufficiently good telescope in various systems. A little blob coming off of a star that accretes onto a neighboring star, such as a white dwarf. When white dwarf gets to be about 1.4 times the mass of the sun, that's called the Chandrasekhar limit. And above that mass, the white dwarf can no longer support its own mass. It's what's called a degenerate star already, but the pressure in the white dwarf is actually caused by quantum mechanics. It's caused by the fact that electrons can't be in the same state. And any smaller than they could be in the same state, but there's a way around that. And that is if the white dwarf gets massive enough by accreting material, then electrons can fuse into protons and become neutrons. Now, the neutron mass is heavier than an electron plus a proton mass, so you need some additional energy, additional from the heat and the pressure from a more massive system. But once you get beyond about 1.4 solar masses, you have enough energy for the electrons to fuse and protons to fuse into neutrons. And then they get around that Fermi exclusion principle, and there's a sudden collapse. So within a span of actually a few seconds, this white dwarf that's the size of the Earth collapses into something that's about the size of the Sandwich Peninsula, and then reverberates, bang, and explodes into, nothing is usually nothing is left. There's no neutron star remnant that has ever been seen from a type 1A supernova. From other types of supernova, usually a neutron star or a black hole remnant is left, but a type 1A, as far as we know, leaves no remnant. It's all exploded into smithereens. And because you're starting out at about the same mass, about this 1.4 solar mass Chandrasekhar limit, that makes it a fairly standard candle. And they have a standard absolute magnitude. And so if you measure their apparent magnitude, you can measure how far away they are. And they have a much higher absolute magnitude than any Cepheid variable star. They're very bright things, so they can be used as far out as the observable universe can go. Still, I could skip ahead. From plots like this, looking at type 1A supernovae, this is way back in 2003, there are much higher statistics plots now, but looking at type 1A supernovae, you can see that the line, what is the line that Hubble saw, which is just like that little line is just the bottom corner of this plot. Looks linear, and that's what you can get from Cepheid variable stars. but you can see as you go at further distances out to much further distances, 7.7 billion light years from Earth, it curves over. Now, some of that curve is expected due to general relativity. You might think, this is why is general relativity just in general causing it to curve? And that's it's because this redshift is getting close to 1. When you're down at 0.1, it's a redshift is a small parameter, but it stops being a small parameter once it gets close to unity, and thus just due to pure general relativity, without considering any dark energy, it causes a curve. But the curve you expect, if there were no dark energy, would be this dotted line below the straight line and below the dashed line in this plot. The dotted line, that 1, 0. That's omega matter, and omega lambda. Lambda is dark energy. Another name, the original name is a cosmological constant. It might still be a cosmological constant, but that is a form of dark energy. If there's no dark energy, omega lambda is 0, and the universe is matter dominated, all matter, and that omega m is 1. Now, this doesn't fit that dotted line, as you can see. It fits the solid line much better. Now, in that solid line corresponds to 75% of the universe, the mass energy of the universe, where mass and energy are treated as equivalent by E equals mc squared. That 75% of the mass energy is due to dark energy, and only 25% is matter. And that matter includes not just regular matter, but also dark matter. So, most of it is actually dark matter, but dark matter itself is only, it's only 20% of the total mass energy of the universe. The dark energy is 75%. It's the big heavyweight there. So, so back to the plot. This pie chart of what the universe is made of in simple terms. It's about 75%, a little less than 75%. That's 73% thereabouts. Dark energy, about 23% cold dark matter, and about 4% atoms. Now there are, a few other things. There's, some radiation. There's some neutrinos, which are a form of hot dark matter, but those are small. Those are small, much smaller components of the universe. Much less than 1%. These three are by far the largest components of the universe. Now, a little more about what dark energy is. So, in 1917, given results, earlier from what we have time to talk about, but the Michelson-Morley experiment showing that there's no luminiferous ether, and thus there's must be something causing light to always look like it has the same speed, to always actually have the same speed, no matter how you aim it or where you aim it. So that in order for that to be the case, how it doesn't depend on the speed of light is always the same in any reference frame. You need relativity, and when you add gravity, you need general relativity. Because special relativity, it's once you add gravity, you need to account for the fact that photons actually are attracted themselves to mass and to energy itself. So for photons, well, they're of course, bend around black holes, but they also bend around any source of mass, or really any form of energy. Concentrated energy will cause photons to bend. General relativity is needed to mathematically incorporate that. And when Einstein came up with general relativity, formalized it, he came up with what you might remember from long ago when you hopefully took calculus. You hopefully remember something called a constant of integration. So a constant of integration comes up when you integrate something in an indefinite way, and it's just there. You need to have limits of integration to determine what that constant of integration is. And constant of integration, well, Einstein had to integrate, of course, in creating his field equation, what are called field equations of general relativity. And there was a constant of integration that came. And Einstein called this constant of integration the cosmological constant. What it corresponded to is the energy associated with the vacuum. So the amount of energy, you could measure it in joules per cubic meter of empty space. Now, of course, that can't be very big, or else the universe would have had a very different history, and we wouldn't be alive today. So even back then, he knew it had to be small. But in order for the universe to be static, which is what Einstein thought before Hubble published his discovery of expansion of the universe, in order for the universe to be static, you actually needed a positive cosmological constant to balance out the gravitational attraction of the mass in the universe itself. So in 1920, but then so that it stuck with the constant of integration, cosmological constant, which needed to be positive in order to keep the universe static. But when Hubble discovered the expansion of the universe, Einstein, this is often related and sort of misrelated historically, incorrectly related. He call it his biggest blunder. But it wasn't a blunder, and he knew it wasn't a blunder to incorporate a constant of integration. That's not the blunder. His blunder is thinking the universe was static, but it was rather, there's a rather subtle reason, because it actually, did seem sensible for the universe to be static back in 1917, and that was because the proper motions of stars were small. Stars and nebulae, they're small. They're fast compared with walking speed, but they're small compared with the speed of light. Now, what Einstein, the blunder was, so it seemed like it should be sensible, but the blunder, a very subtle blunder in that, just because the looking out two-dimensionally and seeing that the universe isn't spinning around and moving doesn't necessarily mean that it's static. You can still look out on a two-dimensional projection of the universe, and it will appear to be static, even if it's expanding in an even way, like the surface of a balloon. As it gets blown up, it'll look, at least in a two-dimensional projection, things won't be moving around. But only if you look out at the recession velocities will you start to see that the universe isn't static. And that was the key thing. It's really a symmetry principle. Einstein was thinking, if you don't see any motion, his blunder was that if you don't see any motion, symmetry between the axes of the universe, if the universe is homogeneous, it must mean it's static. But he didn't, his blunder was that it doesn't violate any symmetry principle if there's an even expansion of the universe. It's still, there's no favored axis or favored direction within the universe. You can still have a homogeneous isotropic universe if it's evenly expanding. That was his blunder, of course. Einstein, that would be a natural thought for anyone. Einstein realized he called it a blunder because he thought he should have realized that. Just from mathematics, you could see that it wouldn't violate a symmetry principle to have that form of expansion. But so you didn't need it. You don't need the that cosmological constant term in order for the universe to be constantly expanding, but there should be a deceleration, a small deceleration parameter from the expansion, from the attraction of the matter to the rest of the matter in the universe. So the universe should be decelerating if there were no cosmological constant. But of course, it's still, of course, even though Einstein, called it his biggest blunder, he wasn't calling the cosmological constant his biggest blunder. He was really calling, static universe was his biggest blunder. So he did. That's how it's misrelated. He didn't really mean to just take this although it's not really needed at that point. It was consistent with zero, but he knew it still should be left in if something turns out maybe the universe isn't decelerating. It wasn't, telescopes weren't large enough or sensitive enough, and it wasn't known that type 1a supernovae, the typing of supernova wasn't around at that time. It wasn't known that they could be used as standard candles. It took until 1998 to extend Hubble's diagram out to much further distances using type 1a supernovae and find that the universe was not decelerating, it's accelerating. So the correct curve in this is that dark energy is dominant. It's dominant. And as the age of the universe increases, the universe will not just expand, but accelerate into what is known as a heat death. But we don't have to worry about that real soon. Not going to happen very soon. Many billions of years. But if you want to turn this into a mass, into a density, turn the energy per volume into its equivalent mass by E equals mc squared, and turn that it's very small. The energy, the mass energy in the vacuum, it's really small, but it's enough. When you sum it up over the whole universe, it's more mass than the rest of the universe combined. About 3 times as much. So what you can see here out on the edge is an image of a type 1a supernova on the edge of this galaxy. This is a HST image from over a decade ago. And you can get a pretty decent measurement of distance, and thus by measuring the redshift of the host galaxy of the type 1a supernova, thus you can get what's called the Hubble plot, the distance versus redshift, and thus see how the universe is expanding. So what's the main limitation here? Main limitation is brightness. You might think it's the it seems it's more abstruse to measure the redshift, but it's actually much more precise. You measure the redshift, the uncertainties on these redshifts. These are large fractions of the speed of light. If you can turn this into a velocity, recession velocity is a large fraction of the speed of light, and the uncertainty on that 3 times 10 to the 8th order of 1 times 10 to the 8th meters per second. The uncertainty on that is of order 10 meters per second. You can measure redshifts, measure recession velocities to a precision of about better than a part in a million. So the uncertainties on this x-axis, this by the way, the axes on this plot are flipped compared with the way Hubble used them. The distance corresponds to the magnitude, and the redshift corresponds to the redshift. So it's the x and y axes are flipped. The uncertainties are all in the magnitude. Now, that's just measuring brightness. Why is that? Why are there such big uncertainties on the y-axis on these? And that's a very good question. It's because it's hard to calibrate telescopes. It's very hard to calibrate what's called photometry of telescopes. Photometry, brightness, it's magnitude. And that is the largest source of uncertainty in the measured cosmological parameters from type 1a supernovae. And unless this gets improved, this is already, well, back in 2003, you can see that statistics, the number of type 1a supernovae, if you added more, the statistical uncertainties from the number of them was the dominant. But just before 2010, they collected, instead of having order of 50 supernovae, by then it was order of 1,000. And statistics, the uncertainty due to the supernova statistics became subdominant. The largest uncertainty was the magnitudes of these supernovae. There's the uncertainty on the magnitudes. And really, it's the uncertainty of the magnitudes, say the flux, as a function of color. Because if what this really depends on, or the cosmological parameters really depend on, is the tilt in this. So if what you're calling a watt, or really, or what you're calling magnitude 20 in the red, as it's further redshifted, versus what you're calling magnitude 20 in the blue, is when it's closer to us. So further away, the more redshifted gets redder. If that's shifted a bit, if it's the Hubble curve gets tilted because of that, you mess up the cosmological parameters. And that's the uncertainty on that tilt is the dominant uncertainty. So you need magnitude standards as at different colors of the spectrum that will calibrate that bias. Make sure you don't it isn't biased, and also the uncertainty. Make sure the uncertainty is as small as possible. Oops. All right. So as mentioned, we're almost done here. Orcasat was launched out of that NanoRacks launch system on board the International Space Station at the end of 2022 and entered into a fairly ISS-like, of course, not exactly the ISS, because it didn't crash into the ISS, of course. It was aimed out of the ISS toward at a 45-degree angle between the back of the ISS and down toward Earth. And ejected at about 1.5 meters per second. And that orbit, well, it takes all over the Earth except for the poles. And that's good because it takes over most optical observatories. Now, the observatory that you see pictured here is the Weir Observatory, which is under construction. 5 years ago, we thought it would be done by this point. And Weir Observatory, which back then was called LSST, and still the survey. Now, LSST back then stood for Large Synoptic Survey Telescope. Now it stands for Legacy Survey of Space and Time. And that's the name of the survey that the Weir Observatory will do. But Weir Observatory is not done. But that's not a problem. There are a lot of other telescopes around there that are also doing dark energy related surveys. and in other places around the Earth. For example, the Blanco telescope, which is about 10 kilometers north, but only 10 kilometers north of the Weir Observatory under construction in Chile, both in the near La Serena area in Chile. Also, over in Hawaii, Canada-France-Hawaii telescope is an excellent observatory for observing Orcasat. Now, it would be nice if Orcasat, you could just take your 12-inch telescope, your typical 12-inch telescope, and take it out and observe Orcasat. You can't do that. It's not bright enough. And that's because there just isn't enough power on board to make a really bright source. And also, just as importantly, even if it were somehow that bright, you'd need you need kilowatts to be observable with a little portable telescope. It's very hard to observe because it streaks across the sky. It's much faster than the motion of the sky as the Earth turns. It's about 1 degree per second, whereas just the motion of the sky is, of course, over about 15 arc seconds per second. It's hard to observe. You need both a very big 4-meter telescope or above. Even the Plaskett, we have not really tried because weather hasn't been good. But even the 1.8-meter Plaskett is not would not be sufficient to observe it. But 4-meter telescopes are. But not just even any 4-meter telescope. You want a 4-meter telescope with a large field of view, because the uncertainty on the orbit, even though the orbit does get updated about twice a day by NORAD, is still the uncertainty is a few arc minutes, several arc minutes, 5 arc minutes or so, and so you need a good 20 arc minute field of view or more, preferably. But Blanco and CFHT and using DE-CAM on Blanco and MegaCam on CFHT certainly satisfy that. Yeah. Oops. So here's the first, and so far, I say, unfortunately, so far the only really good observation we've gotten of Orcasat. I shouldn't say it's the only. We've gotten a beautiful streak of Orcasat, much brighter. That was a good hint that it was that other image there was an issue with it. But this isn't quite the only image we've gotten with Orcasat. We've got one much brighter one, but the much brighter one was due to the fact that that one was only about less than an hour after sunset. It was also on the Blanco telescope, and thus, although Blanco was not in daylight, Blanco was at nighttime. But up at 400 kilometers, there was still the sun still was enough to reflect the Orcasat itself was not in eclipse at that time. It takes about 90 minutes after sunset, if the Orcasat happens to be at the zenith, for Orcasat to be at night beyond the time that that sundown occurs on Earth. But this one, the January 31st observation, this one's the beautiful one. This one is the one that we'll be doing a great analysis on to compare with standard stars and see if it's consistent. The brightness of the streak is consistent with what we expect the brightness should be from our knowledge from NRC, the calibration of the absolute brightness of Orcasat versus as well as its distance, etc. We know how bright it should be, and we can compare that to stars that have been reasonably well calibrated. So what we found, in just one more minute or so, what we found in our 6 months of imaging, or attempting to image Orcasat, our one success so far, hopefully we'll also, our real goal before Orcasat burns up is to also at least get one observation of the 840 nanometer source. Our one good observation was in the R band at Blanco, so red, and so it was, it only saw the 660 nanometer source. That's intentional. The 840 nanometer source, we need the I band of Blanco, and that will very hopefully get a good I band observation, which will observe the 840 nanometer source. Satellites, they have to orbit. You can't have a satellite that isn't spewing out propellant that just stays, goes where you want it to go. Where what you want is some, you don't, observatories have their schedules. And that what you want is a calibration source that goes where the observatory tells it to go, not where it's forced to go by an orbit. You don't want to tell, observatories don't like being told, stop what you're doing and go and look over on the other side of the sky and at this time, and then you can go back to what you were doing. Observatories don't like being interrupted like that. It's for good reason. Interrupts are difficult in every sense of the word. So what you really want is something in the in the sky where you want it to be. And regular high altitude balloons, they can't do that either, but because they need to go where the wind tells them to go. But if you have a high altitude balloon with a little propulsion in it, you can work with the winds, especially if you have a few of them, and put yourself in different places in the sky on a given night. And if you have propulsion, you can, for example, launch out of the back of a pickup truck in La Serena, in Chile, park yourself in at azimuth and certain azimuth range, and be available. Be up at 70,000 feet, 20,000 meters, and be up there to be a calibration source. Have another launch out of the back of a pickup truck, be at another range of azimuth, and calibrate the observatory without having to move the telescope where you don't want it. You move the instead move the high altitude balloon payload where the telescope tells it to go. And you can do that with propulsion, even though propellers aren't super efficient up at 60,000 or 70,000 feet. They're reasonably efficient, and they actually spin faster because of the low pressure up there. So in the future, 20 years from now, which we need to help along, the workhorse for this sort of calibration. Satellites will still be needed, but the real workhorse for this type of calibration will be balloons, specifically propelled balloons. And satellites will still be needed because balloons, while they get pretty high, they don't get above the entire atmosphere, particularly above the OH layer. Another totally separate, but also artificial type of calibration would be what's called a laser photometric ratio star, which is a little like a laser guide star. Now, laser guide stars, which you hopefully have heard of and know of, they calibrate telescopes, but they don't calibrate photometry. They calibrate or reduce point spread function. Totally different type of calibration. Point spread function as blurring, as that increases, it means blurring is increased. Having a laser guide star can do great with reducing that, but you don't know how bright it is. You only would know how bright it is if you knew exactly how much sodium is in the sodium layer at any given time at every given place. But what you can do with the sodium layer is if you excite a different resonance, you can create a cascade, which will create a 1-to-1 ratio between 820 nanometer light and 590 nanometer light. And that can give you another type of photometric ratio that you can get without, well, in addition to having balloons and satellites. That's another thing that one could use and should use, but that has the disadvantage that it has a really big advantage, and it'll be really, really precise. Give you a photometric ratio of about 10 to the minus 4. And this, but the real advantage of I'll be done in just 1 minute. Whoops. So yeah, this is in fact my last slide. The real advantage of balloons and satellites is they can put pretty much whatever colors of light you want up there, whatever you want. Whereas with sodium laser guide stars or laser photometric ratio stars, you are restricted to 819.71 nanometers and 589.16 nanometers in that ratio. Anyway, that's all I have to say. If there are any questions, please let me know. Sorry for taking so long.
Thank you. That's awesome. So is the reason why satellites are better than balloons at doing this just because of the atmospheric turbulence?
I wouldn't say satellites are better. They both have their advantages and disadvantages. So balloons have the advantage that it can stay put and go where you want it to go. It doesn't have to be orbit, but it does have the disadvantage that it isn't above the entire atmosphere. So what you really want, I think, in 50 years of every decently major observatory will have a set of Altair-like balloons, a few, and a small, few pickup trucks to send them out to launch and collect them in, have them land in, and at dawn, launch them at dusk, fetch them at dawn. But there'll be, 1 or 2 satellites for, that are, at a given time that are satellites that also because satellites are much more expensive. So the workhorse will be balloons, but satellites will still be needed in order to calibrate things like the hydroxyl layer in the upper atmosphere that's above where any balloon can get. And the sodium layer itself, sodium does have some absorption as well as emission at 589 nanometers, et cetera. So that's sort of calibration of layers above where balloons can get. You need something above those layers.
And Lauri has a question.
Yes, I was wondering how much each of these, when you put one of them up, you were talking about kind of at dusk and then getting them at dawn. How much does one of these cost to put up?
So the goal is to minimize the expendable materials. Certainly much of the helium will be expended. But it's only about the amount of helium that goes into one of these balloons is only about $150. So you recover the payload, it'll fall back. So that will be just a startup cost. It won't be a expendable material. The balloon itself, though, is likely not to be reusable if you use latex balloons. Latex are definitely the cheapest balloons. They're only about $150 a piece as well. So it's not the ongoing costs of these, and that if you use polypropylene balloons instead of latex balloons or small polypropylene balloons, then you could reuse those. So, the ultimate goal would be, and I don't think you could get any less than it costing in expendable materials about at least $100 per launch, even if you recover most of the helium. So per Altair per launch, it's not going to be any less than $100, just for the gas to get the pickup trucks to where you want to launch them, et cetera. It'd be if you have 3 of them, $300 a night, et cetera. But that's not a big cost for major, compared with other costs for major observatories. $300 a night isn't a big cost. A much bigger cost would be startup, making and purchasing eventually. Nobody sells these. The only country that has made the country that has made the most progress toward this type of balloon, unfortunately they have misused them for not scientific purposes so far, but China has made certainly a lot of progress in these types of balloons. But we want much smaller. We don't need anything like that ridiculously gigantic Chinese balloon that overflew North America several months ago. Much smaller, but propelled, but used for productive and useful for everyone, useful for humanity's purposes.
Yeah, your Altair balloons, you haven't by any chance spotted any F-35?
No. And one thing I need to buy with some grant money this coming month, we haven't been flying Altairs for past several years, so that certainly we haven't run into any issues. But in order to ensure that we don't ever run into any issues like that, we're purchasing a transponder for our test Altair, as well as what's called an ADS-B transceiver, which is the way that the air traffic control can ensure that you have a not an incursion, but a well-identified good non-threatening object.
Thank you very much. Thank you, Justin Albert. That was most interesting.
Thank you very much for having me.
You bet. And our next presenter is Nathan. And from Nathan, here is some information. The topic is his science fair project. And it's called I Need More Space-Time. It is known that Hubble's constant, the rate of expansion of our universe, is approximately 73 kilometers per second per megaparsec. It is also known that the rate of expansion was slower in the past and will accelerate in the future. My project aims to show that it is possible to predict the time and process by which our entire universe will end, using only a backyard telescope and a personal camera. By observing nearby and distant type 1a novae in galaxies beyond our gravitationally bound Virgo supercluster, one can detect the change in redshift and brightness between them. Taking into account the delay from a finite speed of light, it is possible to determine the galaxy's distance and recession velocity. I aim to calculate and verify the rate at which our universe's expansion is changing over time and the ultimate implications the expansion rate has for humanity. Nathan, over to you.
Thank you. Yeah, so first off, that original project plan quite quickly fell apart because I realized that type 1a supernova explosions are around 15,000 times fainter than what my iPhone can detect with my telescope. So it actually ended up being analyzing the data from the Wiseman Observatory, because they had just dropped a depository of data. Although I guess it was not for naught, because there was an effort that I received a tremendous amount of help with from David Lee and Joe Carr, as well as Lauri and Samuel Fielder. Thank you very much to all of you. Yeah, they were kind enough to use the SLU online observatory to capture images of galaxies that contained type 1a supernova explosions in them. Unfortunately, even with the SLU observatory, which is one of the largest amateur telescopes in the world, the galaxies were still just specks. The supernovae within them were invisible, so I decided it wouldn't be a first-hand data project after all. Second of all, it appears that most of my topic has already been talked about. Anyway, yeah, so how do I hook this up to the...
Okay, so are you in Zoom?
Oh, I'm not even on that, right? Oh, right, screen sharing, of course.
It's okay, Nathan. We like it from you too.
Okay. Oh, I'm not connected to the internet. Wonderful. Okay. Yeah, I guess I'll just talk about it. So essentially, yeah, what I was doing was I was looking into the depths of space, because while we can measure Hubble's constant, which is how fast our universe is expanding currently, what it doesn't account for is the fact that we don't see the current universe in deep space. It takes so long for light to cross the vast distances between galaxies that, you know, what we're left with is we're looking at a distant universe in the distant past. And the further into space we look, the further into the past we're looking. And that's not just galaxies as they existed in the past, that's space itself as it existed in the past, with perhaps a very different expansion rate. And what my project was looking for was how the universe was expanding in the past compared to how it's expanding in the present, to extrapolate into the future. And what I did was exactly what has already been talked about, which is the type 1a supernova explosions, and how you can use those to essentially infer how fast supernovae and their corresponding galaxies are moving away from us. And then by looking, since they all explode once they reach the Chandrasekhar limit, or 1.4 solar masses, they all produce identically bright explosions, more or less, and they all produce more or less identical spectral lines, which means that any difference in brightness is usually a matter of distance, not actual physical differences in brightness between the supernovae. And any difference in spectral lines is usually entirely a matter of redshifting, or a difference in velocity, not an actual difference in spectral lines. That's why they're called standard candles, because they're all more or less the same, which means you can kind of infer distances and velocities just looking at how their spectra and how their brightness have shifted. So I looked at spectrographs that had just recently been looked at by the Wiseman Observatory. And then I measured two emission lines on those spectra, which were the hydrogen epsilon and hydrogen delta, which are very, very prominent spikes or emission lines on type 1a supernova spectra. And usually they have a wavelength of 390 nanometers for hydrogen epsilon and 410 nanometers for hydrogen delta. But on the very distant supernova explosions, the most distant one they looked at, those were up to around 5,000 nanometers. So talking like a redshift factor of around 12, which is an immensely distant galaxy. So I think The galaxies I looked at ranged in distance from around 30 million light years to 40 billion light years, which is around 90% of the way to the edge of the observable universe. So I looked at the redshifting of spectra to figure out how fast they were moving away from us. And then I looked at how dim they were in the sky to look at their apparent magnitude or how bright they appeared, to figure out how far away they were. And then once I'd figured out how far away each supernova was and how fast it was moving away from us, I was able to figure out how fast space was expanding at a given distance. And what I found was that the Hubble constant, or how fast our universe was expanding, was quite a lot smaller in the past. What I found was like, I think 10 billion years ago, it appeared to only be around 20 kilometers per second per megaparsec, whereas now I found it to be, and numerous studies have also confirmed it to be, around 70 kilometers per second per megaparsec. So a substantial increase. And I also found that it appears to be increasing at a sort of an asymptotic inverse function where it's accelerating toward infinity as its inverse goes towards zero. So sort of a 1/x function. And what I found the implication was, if it really is like an asymptotic sort of thing, it's eventually going to reach infinity, which is not the best situation for us if we like existing. So what the conclusion I drew from the data I collected was that in around 14 billion years, the Hubble constant I found when I extrapolated would reach infinity. And that in cosmology is known as the Big Rip, where everything just gets torn apart in a completely catastrophic, non-Hollywood style ending. Now, that is contrary to the consensus in cosmology right now. And I just recently figured out, this was after the science fair too, I figured out why my data were contrary to the consensus in cosmology. That's because of an error that happened in my data set where, and I had my eye on this from the start, I just kind of didn't think too much of it, which was that, you know, we kind of have this assumption that an object 1 light year away, we see it as a year in the past. An object 10 light years away, we see it as 10 years in the past. So I just kind of applied that rule to my entire project. And our observable universe, I mean, we know it to be 93 billion light years across, or 46 billion light years in radius. But our universe is only 13.8 billion years old. So one of the weird implications of that was those galaxies that were 40 billion light years away were 40 billion years in the past, which is like several dozen billion years before the Big Bang. And I just kind of took that as artifacts and still used it as an extrapolation, even though it wasn't technically valid in its actual placement in time. But what I later found was our observable universe actually isn't 46 billion light years in radius. That is what it is now. But we don't see light from 46 billion light years away. We see light from galaxies that are now 46 billion light years away, but we're seeing the past versions of them that are, of course, less than 13.8 billion light years away in their past images, their ghostly light that we see in the sky right now. So that was a bit of a misunderstanding on my part. And I am interested in rerunning my data through the process that I did to see if it correlates with the current consensus from the WMAP satellite, which is that our universe's expansion, the Hubble constant, is actually, it's increasing, but the rate at which it's increasing is not accelerating. It's sort of getting bigger and bigger, but at a lesser and lesser rate. I don't know if that makes sense. It's accelerating, but the acceleration is decelerating. So it's still an accelerating universe. But yes, the comment that just came in, it does not predict that a big rip will happen. It predicts, like was said earlier, a heat death or a universe that keeps expanding indefinitely that just gets colder and colder and colder and emptier. So yeah, I'm glad, I was very glad to find that discrepancy or perhaps a possible explanation for it. And I am eager to try and rerun the data to see if it correlates now, or if it doesn't, perhaps another reason why there's discrepancy. But anyway, yeah. So thank you.
Thank you very much, Nathan. Always good to be able to look back and analyze what we've done and make it better. Any questions for Nathan?
An important point of that's a very important, when you measure a magnitude, you're of course looking out into the past. When collaborations do this type of analysis, you have to change the magnitude. You have to modify the magnitude into what's called the rest frame. So that the magnitudes that are plotted in the publications that I showed from the high redshift supernova team and supernova legacy survey, etc., where they're based on what's called the rest frame B-band magnitude. You shift the magnitude into the rest frame by doing what's called a K correction. So if you Google K corrections and magnitude, K correction magnitude, you may get something that's helpful for what you're doing.
Cool. I had not heard of that, so that could be another possible reason for the discrepancy. Yeah, I mean, once you're dealing with like so far back in time that the universe itself was not the same as it is today, everything is offset, I guess. Like there's a whole bunch of corrections that need to be made. And perhaps that's the limitations of simply doing an extrapolation without taking all those into account. Like, I guess you can only go so far with just drawing a line and extending it. So yeah, I'd love to look further into that.
Lauri, you have a question.
Yes, Nathan, what did some of the judges say to you that were helpful? Like, because you did have a few of the judges come around and talk to you about your project for the day, on the day of the science fair. So what were some of the things that is deemed helpful? Like Dr. Albert was just giving you something there. Did you get some other things from some other people?
In the feedback, I definitely received numerous official studies that said otherwise to what my project had revealed. So I got a lot of a lot of contrary results, which was helpful in, verifying that there was a major discrepancy. And then another judge who was a mathematician said that in the integration equation that I derived to measure galaxies, one of the variables should have been 0 or something, which didn't actually affect the result. It was just part of the notation. I'm trying to remember. I think it was largely results that had different results to my analysis. And there were many, and not all of them even had the same results to each other, which just goes to show how big an open question this is in cosmology right now. But yeah, it's wonderful how big a mystery this is.
Thank you. David, you have a question. David, you're muted.
Just a couple of goofy questions. It was a really nice project, Nathan. So my first goofy question is, why is it called a constant if it's not constant?
Yeah, so it's a constant in space at this present moment. In fact, I believe that many astronomers don't like to use the term Hubble constant at all because they call it the Hubble parameter. but yeah, so every point in space at this moment in time is expanding at a constant rate. So it's like a grid that is growing at the same rate everywhere. But the distant points on the grid, we cannot see them at this point in time because it just takes so long for their light to reach us. And there's nothing about the Hubble constant that is constant throughout time. And it's really just about being constant in space at this one time.
Okay, I'll buy that. And my other goofy question is, so you mentioned the radius of the universe. So when I think of radius, I think you might have mentioned the spherical geometry to it. So if you look at a galaxy that's 13 billion light years away, I presume if you had a telescope pointed back at us from that galaxy, we would be 13 billion light years away from it. So what if the person on that galaxy actually rotated their telescope 180 degrees away from us? Would they see galaxies that are 13 billion light years in the opposite direction?
I suppose that's really another open question, which is how large is the actual unobservable universe? And after I try to answer this unanswerable question, yeah, I don't know if Dr. Albert has anything
Sure.
to add to this, but
So-
oh yeah, sorry.
Oh, no, well, I mean, so, our horizon, the horizon of our observable universe, the whole universe, we don't know. The horizon is the cosmic microwave background. When we look back and out in any direction, we see the oldest and furthest photons that we can see, and really that we'll ever see, are the cosmic microwave background. That's our horizon. It's basically, it's the edge of the observable universe. It's the dying flame of the Big Bang. That's what you're seeing when you look out at those most distant photons. If you look in photons, you're never going to see any further than that, because beyond that, the universe gets opaque, because you're looking into a flame. The flame is opaque beyond that point. But if you were to, at this present time, somehow, it's 13.6 billion years away. Some planet out there, but at this time, were to look in the other direction, well, probably they would see a lot more galaxies that we can't see out in the other direction. Probably the simplest picture is that the universe is the total universe probably infinite, but we're never going to know that. We don't know if the very basic question that we don't know the answer to is the universe finite or infinite. And all we know is we can see out to the horizon. We don't see an edge anywhere, and there's probably it's probably infinite, but it is one of those questions that isn't answered, and I won't say it won't ever be answered, but it won't be answered simply. But what we can see is our observable universe, and we can even see if you go beyond photons, if you look in gravitational waves, for example, potentially you can see further than the cosmic microwave background. And see remnants of even earlier in our universe. The horizon is which is the cosmic microwave background, is as far as we're ever going to see with photons.
I think I was researching something the other day that cosmologists had a very dramatic term called the end of greatness, which is like at a certain scale of our universe, structures stop being building blocks of larger structures. Like once you get to galactic supercluster filaments, like 600 million light years wide, you just start getting more of the same thing over and over and over again. And you get this like big cosmic web structure that extends uniformly as far as we can see. And like, I guess at that point, we don't really have any evidence to suggest that there's like a border at which it stops. It just appears to keep going forever. So if there was a galaxy 13 billion light years away, looking back at us, I mean, we certainly wouldn't exist from their point of view, because they would be looking at a Milky Way version that existed billions and billions of years in the past. I don't think the solar system even existed back then. So they would just see another dead galaxy. They'd probably call it some obscure name like GN something ... 13303 something. No significance whatsoever.
Thanks, Nathan. Well done.
Miles, did you have a question you'd like to ask?
I hope it isn't obvious, but I just was wondering where is the point that was the Big Bang? And if it's obvious, you could tell me.
There are a lot of theories for that. If our universe is shaped like a sphere, and it's like an expanding sphere, then you could technically say that the singularity was everywhere, because if space is shaped like a sphere and it began as a point, then every point in space was in that singularity and it grew, and now it encompasses everything. So you could say that at time zero, so to speak, everywhere you looked would have been the singularity. And then there's the other theory, which is like eternal cosmic inflation, where space is just expanding ludicrously fast. And then every once in a while, some of this crazy fast expanding space collapses into a normal expansion, or normal as in slower, like we see it in our universe. And then the fallout energy from that collapse forms a bunch of particles and matter, which now composes our universe. And in that case, the singularity would have just happened everywhere all at once, like a giant, because it wouldn't have really been a Big Bang then. It would have been a big collapse from a crazy fast expanding space to a more comfortably expanding space, so to speak. I don't know if I got that right. The theory of eternal inflation. Is that...
So I mean, the somewhat easier question is, where's the Big Bang? It's beyond the horizon. It's the that's further back. It's interestingly not it's only 100,000 years or so beyond the cosmic microwave background horizon. But it's still opaque because the universe was very, very hot then and was flaming hot. It's a plasma rather than so charged, and thus opaque to photons. They just bounce around, and you can't get a line of sight beyond that wall of the cosmic microwave background, that dying flame. So that's why it's obscured to us, the singularity, if there was one, if it was truly a singularity of the Big Bang. You don't see beyond the cosmic microwave background. It's as far back as we'll ever see in photons. So that's a limit of sorts. But it does give it's a heck of a good hint that the universe did start out in a very hot, dense state, in that it is a dying flame. That's what we're seeing with the cosmic microwave background in all directions. So even though it obscures beyond it and obscures the Big Bang itself, it tells us a lot about those really early conditions, especially what are called the anisotropies that WMAP and earlier Kobe and more recently Planck have measured. Tell us a lot. Those slightly hotter and slightly colder spots within the cosmic microwave background, they tell us a huge amount about the universe. It's not the only cosmological probe there are type 1a supernovae, as mentioned, are completely separate cosmological probe that tell us a lot about the expansion history of the universe beyond after the cosmic microwave background. But the probe that tells us about the universe at its oldest state that we can currently get a decent picture of is cosmic microwave background itself. Another important probe that that's separate from either of those is the ratio of hydrogen and helium in the universe. And that tells us, that's another separate piece of evidence that the universe started out in a hot, dense state, because the 75% hydrogen, 25% helium is exactly what you get, that ratio, if you start out with a soup of quarks and gluons. You can show that mathematically from strong interaction, strong and weak interactions, and electromagnetism, that when you start out with a soup of quarks and gluons and you let it cool, you end up with 75% hydrogen and 25% helium, and just little bits of other stuff. And that's what we observe. All the other stuff was made in stars later on. But the base material of the universe is that ratio that comes out of nucleosynthesis. So that's another very strong hint that the universe started out in a hot, dense state. But it's still the Big Bang itself and anything beyond the cosmic microwave background in terms of actual observation, direct observation, is obscured, at least in photons.
That's very annoying.
Yeah.
It would be very nice if, since you had an explosion from singularity, you could just trace back all those acceleration points back to a point.
Gravitational waves, but unfortunately the gravitational waves from that early era, hopefully probably not within either of our lifetimes, but hopefully those early gravitational waves, those are not obscured by because those aren't photons. Those will give hints of even earlier. Now, before that, probably before LIGO and its successors observe in gravitational waves hints of the early universe, what the LIGO observes are just black hole collisions in the modern universe. Not mostly cosmology, but mostly, or at least not directly, but just interactions between black holes and also with neutron stars amongst themselves in the more modern universe. But hopefully, eventually, the successors of LIGO will be sensitive enough, even and maybe LISA as well in space, to detect the what's called the stochastic background from inflation, from the gravitational waves from inflation. Before that occurs, we might, and even by around 2030, see an imprint of those gravitational waves on the cosmic microwave background itself in what are called B modes. B modes are so that the anisotropy, the hot and cold spots of the cosmic microwave background is not all that you can learn. There's more to what you can learn from the cosmic microwave background, because there's also polarization. The cosmic microwave background is also polarized, and that and the map of polarization, it's a very small polarization, but a map of the polarization gives you even more information. And if you see swirls, what are called B modes, because been separated out into curl and divergence. The curl is what are called B modes, and divergence is E modes. B modes are indications, at least at certain angular scales, large angular scales, of gravitational wave imprint on the polarization of the cosmic microwave background itself. And that's what microwave telescopes such as BICEP at the South Pole. Now, you may have heard, might even remember, about 7 years ago, BICEP claimed that they saw B modes. Now, but it was
they later retracted their claim of that, after being clearly shown by others that this was just due to polarization from dust in the galaxy, which is also polarized due to magnetic fields in just our local galaxy. But eventually, so there's all sorts of foregrounds that can spoil that measurement. But eventually, the B modes, maybe around 2030 or so, the B modes will be measured, those foregrounds will be properly removed, and we'll see a small but significant B modes from gravitational waves imprint on the cosmic microwave background. And that's likely to happen earlier than a direct detection of the gravitational waves at gravitational wave observatories like LIGO, which might be more like 2050 before that happens. But we might see that, and that will be there'll be Nobel Prizes that'll come out of that, definitely, because that will be a clear smoking gun of inflation. Those B modes in the cosmic microwave background polarization. But there's a lot of systematic effects that can come into that.
Nathan, thank you very much for your presentation. And I love your t-shirt, being a musician, E equals F flat. Yep, perfect. Yep. All right. Do we have any announcements? Any SIGs this week, David?
No, not as far as I know. I think the next one is probably David in a couple of weeks for the astrophoto one.
Yeah, a couple of weeks out.
Yeah.
Okay, thank you. And Lauri?
Lauri has her hand up though.
Yes.
Yeah. I just wanted to say thank you to everybody who came to the GA. We had a great time. We had some wonderful, wonderful speakers, one of which was Nathan and one of which was Randy. So we were really happy to have that. And David, thank you for helping out. And on Friday night, we had Brian Barber and Ruhi Jan Mohammed. We had Dan Posey and David and myself, and we gave the tour of the Plaskett telescope and a little bit of the gallery and things that were going on to the group on Friday night for the observatory. So we were really happy to be able to do that as well. So our next star party for the FDAO is this coming Saturday night. We are completely sold out again, and we've got waiting lists and people desperate for tickets. So we'll have lots of people there. Our last one, we were just about filled. I think we had about 190 people come up out of the 200 tickets. So that was a really good time. We'd love to have you people up. I'd love, if it's a nice night, please come up and bring up your telescope. Bill, you had a grand time on the deck. I remember, like on the last star party, you were doing wonderfully out there with everybody. And just if people want to come, bring their telescope, and you don't even need to bring your telescope, just bring a pair of binoculars. We've got some telescopes that you can put up and just simply chatting away and talking with other people. But I also just wanted to say that Melissa and Clint, I've just lost their last name. Help me. Tupper, thank you. They have agreed to look after the welcome desk at the FDAO for Saturday nights. So you might be getting phone calls from them to see if you could come up and help us with that. So anyway, enjoy the rest of the week, and we might see you up on Saturday night. Thank you.
Thank you, Lauri.
I'm still looking for warm bodies to help out at the scouting event at the end of the month. So it's May 27th, I think it is. Whatever the Saturday is at the end of the month. out at Camp Bernard. You can contact me. You can use my national rep email or WC Weir at Shaw. And like I said, you don't need to have any equipment. You just need to have enthusiasm, and I'll supply all the rest. It's a lot of fun, and it's more like, it's not too hectic, actually. It's pretty laid back.
Thank you, Bill. David, you have a comment?
Oh, I just, I'm going to next week. I just want to put point your direction to the Island Star Party website on the RASC website here for details. It's the next major event we'll be having as a group, but it's not until August 11th to 13th. I'll be lots of things planned. We just got our permit for the park, so it's all ours, and for that weekend, and I'll be providing details next week at this meeting, and also a bit of a call for volunteers to help set it up.
Thank you, David. Anybody have anything else they'd like to share?
I've got some images that I did put together for International Astronomy Day, but it didn't really work out.
Maybe not tonight, though. Maybe not tonight, Ken, because we're just about on our deadline here.
Oh, okay. Yeah, we'll do it next week.
Yeah.
Okay,
And thank you, Margie, for hosting.
you're welcome. Thank you to everyone, and we'll see you next week when we have another wonderful speaker. Good night.
Thank you, Dr. Albert.
Thank you.